The Orion spacecraft's heat shield is essential for protecting astronauts from extreme temperatures during re-entry. With a diameter of 16.5 feet, it is the largest and most advanced heat shield of its kind. Weighing 1,000 pounds, it can withstand temperatures up to 6,000 degrees Fahrenheit, ensuring safe re-entry at speeds 25 to 30 times the speed of sound. The GE Treveni 35 megawatt steam turbine assembly showcases advanced engineering and precision. Featuring high-precision aerodynamic blade profiles, the turbine ensures optimal performance and efficiency. It includes a compact 20-stage design with a 7-stage high-pressure section and 3-stage labyrinth covers to improve steam efficiency. Enhanced labyrinth seals reduce leakage, while the inner high-pressure casing provides structural integrity. The rotor undergoes rigorous high-speed balancing and resonance testing to guarantee reliable operation under demanding conditions. Every component is subject to strict testing procedures, ensuring durability and peak performance. This combination of innovation and precision engineering makes the GE Treveni 35 megawatts turbine a powerful and efficient solution for modern energy generation. A comprehensive, structured service process for rotating equipment ensures efficiency, reliability, and extended equipment life. The process begins with an electrical inspection and test, where the equipment is thoroughly analyzed for wear, imbalance, or faults. This is followed by a detailed life assessment, which determines the remaining life and creates a suitable maintenance plan. Next, based on the diagnostic results, Sulzer implements performance upgrades using advanced technologies to improve operational efficiency and reduce energy consumption. When repairs are required, rotor repair and overhaul services include precision welding, protective coatings, and quick repair techniques to restore functionality quickly. During repairs, high-quality components are replaced to ensure long-term durability. All processes are supported 24/7, allowing for immediate response in critical situations. The production of a saddle-shaped ship hull plate using a Neyland cold-forming press is a highly specialized process in modern shipbuilding. Aimed at producing large, curved steel panels with precision and efficiency. This process is essential for shaping parts of the hull where complex double-curved geometries are required, such as at the bow or stern of a ship. The process begins with selecting an appropriate steel plate from the material inventory. The plate, often several meters in length and width, is cut to a predefined size based on CAD drawings and design specifications. The selected plate is then transported to the forming station, where the Neyland cold press machine is located. Unlike traditional hot forming methods that rely on heat to make the steel more malleable, Neyland's cold forming technology uses purely mechanical or hydraulic pressure to bend and shape the plate at room temperature. This approach retains the mechanical integrity of the steel, avoiding metallurgical changes that can occur under high temperatures. The steel plate is carefully positioned and clamped onto the working table of the cold press. Operators then initiate the forming sequence using the CNC interface, which controls the position, pressure, and duration of each press stroke. In the case of a saddle-shaped form, the press must perform a series of bends with varying radii along two axes, longitudinal and transverse. creating a compound curvature that mimics a saddle profile. The process requires multiple passes. Each stroke of the press targets a specific zone of the plate, gradually bending it toward the desired shape. Between strokes, the plate may be repositioned, and forming tools such as specially shaped dies may be swapped to match the curvature required. Precision sensors and laser measurement systems are integrated to monitor curvature and deformation in real time. The system uses this data to automatically adjust pressing parameters, ensuring consistent quality and accuracy. Once the desired curvature is achieved, the formed plate undergoes quality inspection. Technicians use 3D laser scanning or coordinate measuring machines to compare the actual shape with the original 3D CAD model. This comparison ensures that the formed panel meets the dimensional tolerances required for assembly. If the plate passes inspection, it is moved to the next stage, either assembly, welding, or storage until final integration. The saddle-shaped plate may be joined with other formed panels to construct a complete hull section. Neelan's cold-forming press offers a highly efficient, repeatable, and energy-saving method for ship hull plate forming, reducing production time and improving product consistency while supporting the automation goals of modern shipyards. Wärtsilä is a global leader in marine power and energy solutions, and its operations in the Netherlands represent a critical hub within this extensive network. With over 1,500 employees and multiple facilities across the country, Wärtsilä Netherlands serves shipbuilders, operators, and the decentralized energy market with world-class engineering, manufacturing, and maintenance services. One of the key facilities is located in Drunen, which acts as a global knowledge center for the design, production, and service of propulsion systems. Here, Wärtsilä manufactures a wide range of propulsion equipment, including fixed and controllable pitch propellers, propeller shafts, rudders, steerable thrusters, and water jet systems. Each propeller is individually cast and hand-finished to meet exact specifications, ensuring long-term performance. The Drunen site also specializes in the repair and reconditioning of damaged propellers, offering ship owners reliable and sustainable service options. Wärtsilä's collaboration with major maritime companies further illustrates its influence. Companies like Royal Wagenborg, which operates a fleet of 160 vessels, rely heavily on Wärtsilä engines and propellers. Two-thirds of its fleet is powered by Wärtsilä engines, and nearly all vessels use its propulsion systems. This partnership showcases Wärtsilä's capacity to supply reliable, standardized, and globally trusted power solutions for commercial shipping. In Schiedam, near the port of Rotterdam, Wärtsilä operates its largest marine service center in the Netherlands. This facility provides a full range of support services, from engine overhauls and reconditioning to automation solutions and spare parts logistics. Its proximity to Europe's busiest ports ensures fast and efficient support for urgent marine service needs. Other key locations include Zwolle, home to an automated logistics center that stores and dispatches spare parts worldwide. In Groningen, Wärtsilä operates a specialized workshop that reconditions vital two-stroke engine components, such as piston crowns and cylinder heads, regardless of their brand. These components are rigorously inspected, repaired, and returned with a full factory warranty, maintaining engine integrity and reducing the need for complete replacements. The sale facility focuses on delivering Wärtsilä power plant solutions for decentralized energy production, catering to urban, industrial, and remote areas. It also supports maritime propulsion and maneuvering systems for all kinds of vessels. The site has the ability to repair, manufacture, and recondition every kind of four-stroke engine component, ensuring comprehensive lifecycle support. Overall, Wärtsilä's network in the Netherlands is an essential part of its global service organization, combining innovation, precision manufacturing, and lifelong support. Whether powering ocean-going vessels or decentralized energy facilities, Wärtsilä in the Netherlands ensures performance, reliability, and sustainability for clients across the globe. The process of building a Carnic powerboat is a carefully planned and detailed journey, combining modern technology, high-quality materials, and exquisite craftsmanship. It begins with a conceptual design phase, where highly skilled engineers and designers use advanced CAD/CAM software to create detailed 3D models. These digital designs define every curve and component of the boat, from the hull shape to the cabin layout and the smallest structural details. Once approved, the design is converted into precise physical molds using a precision 5-axis CNC milling machine. These molds become the foundation for the composite construction of the hull and other structural components. Carnic uses closed mold transfer techniques to manufacture the hull, a method that ensures consistency, reduces emissions, and increases the strength-to-weight ratio of each component. High-quality vinyl ester resin is used for durability and resistance to water penetration and osmotic blistering, making the boat ideal for use in both fresh and salt water. After molding, the hull is internally reinforced with a prefabricated composite grid structure and injected with buoyancy foam, which improves strength, stability, and buoyancy while maintaining a light weight. The assembly process includes the installation of critical systems such as fuel tanks, wiring, plumbing, and navigation equipment. Special attention is paid to every fitting and fastener. Instead of screws, Carnic attaches windows and hatches with high-performance adhesives, providing a cleaner appearance and better sealing. Stainless steel components, such as handrails and fasteners, are fully welded, providing superior strength and a polished finish. The glass used in the cabin and control platform is laminated automotive-grade safety glass, which adds both clarity and impact resistance. Inside, the attention to detail continues. Modular seating, ergonomic controls, and high-quality upholstery are all individually designed for comfort and long-lasting durability. Each model is designed for ease of movement and maximum use of space. Whether it is a family cruiser, fishing boat, or luxury day boat, before any boat leaves the factory, it undergoes a rigorous quality control process with over 150 individual inspections. This includes structural integrity testing, leak detection, electrical system verification, and a final check for aesthetics and finish quality. Customization is another cornerstone of the Carnic experience. Customers can personalize many aspects of their boat, including hull color, cabin layout, engine options, upholstery, and electronics. This flexibility ensures that each boat not only performs well on the water, but also reflects the owner's unique lifestyle. With a combination of precision engineering, premium materials, and elegant design, every Carnic powerboat is built to deliver reliability, safety, and enjoyment for years to come, making it a trusted choice among boating enthusiasts worldwide. Finally wrapped in nylon and net for delivery, the production of an engine block using sand 3D printing, often through binder jetting technology such as that offered by Printy 3D, represents a transformative shift in casting methods. Traditionally, engine blocks are cast in metal molds formed from complex cores and patterns. With sand 3D printing, digital designs are directly translated into physical sand molds without the need for tooling. The process begins with a CAD model of the engine block, which is digitally sliced and prepared for printing. Using a binder jetting 3D printer, thin layers of specially prepared silica or ceramic sand are evenly spread over a build platform. A print head then selectively deposits a binding agent onto the sand layer, solidifying it according to the desired geometry. This layer-by-layer process continues, gradually forming the complete negative mold of the engine block, including intricate internal cavities like cooling channels and oil passages. Features that are difficult to achieve with traditional methods. Once printing is complete, the unbound sand is removed, leaving behind a high-resolution sand mold ready for metal casting. After post-processing, molten metal, typically aluminum or cast iron, is poured into the mold. Once cooled and solidified, the mold is broken away, revealing a highly detailed block casting engine. Sand 3D printing offers unparalleled design freedom, reduced lead times, and cost-effective prototyping or low-volume production. The image showcases a highly automated production line in the precision engineering industry, featuring the integration of industrial robots and specialized press machines. Key stages include the MX350 robotic arm, bearing press machine, part repositioning equipment, oil seal press, and a large hydraulic press. This assembly line is optimized for handling and assembling large mechanical components, such as gearbox housings, ensuring high accuracy, safety, and productivity. The system reflects advanced manufacturing processes where automation enhances consistency, efficiency, and overall output in a modern industrial environment. Flowform wheels combine the strength and performance benefits of both cast and forged wheels. Thanks to a specialized manufacturing process called flowforming. This combined method creates a wheel that is lighter than a traditional cast wheel, while still maintaining improved performance characteristics. Flowform wheels cost about a quarter of a typical HRE forged wheel, making them a popular choice among those seeking high-end performance on a budget. The design process for each wheel begins with a sketch or concept by the design team. Multiple design directions are explored, and the team then narrows them down to a final concept. This design is then converted into a 3D model using computer software, which is fine-tuned to ensure it meets the specific technical requirements of the target vehicle. The durability of the design is tested using finite element analysis, CA, which simulates real-world stresses to ensure the design will hold up under normal use. Any necessary adjustments are made based on the FEA results, adding or removing material to improve performance and durability. Once the design is approved, the factory creates molds and begins the manufacturing process. The raw material for flowform wheels is A356.2 aluminum alloy, which is known for its strength and favorable casting properties. The alloy is melted in a furnace at approximately 1400 degrees Fahrenheit, filtered and degassed to remove impurities. Once the aluminum is at the desired molten state, it is poured into a steel mold, with the wheel face placed on the bottom to create a stronger spoke. The casting is then quenched in water to cool and solidify. Once the casting has cooled, it undergoes the flow-forming process. The casting is heated and placed on a preheated mandrel, forming the rim. Rollers apply pressure to squeeze and stretch the aluminum skirt into its final shape, enhancing the wheel's impact resistance. This step also improves the overall durability and performance of the wheel. After flow forming, the wheels are heat treated to refine their mechanical properties. This heat treatment process ensures the aluminum reaches the correct hardness. The wheels are then subjected to a number of quality control tests, including X-rays to detect any internal voids or cracks, and machining processes to complete the rim profile, including lug holes and valve stem holes. The wheels undergo concentricity checks to ensure proper fit before moving on to the cleaning and finishing stage. Flow-form wheels are then powder-coated for durability and finished with a clear coat for a satin finish. The wheels undergo rigorous testing to ensure they meet German TÜV standards, including radial fatigue, cornering strength, and impact resistance. Once they pass these tests, they undergo final inspections, including color and finish checks, before being boxed and shipped. The production process of the BMW 3 Series F30, the sixth generation of the iconic sports sedan, exemplifies BMW's commitment to blending cutting-edge technology, precision engineering, and innovative design. Assembled primarily at BMW's state-of-the-art facility in Munich, Germany, and other global plants, including Vietnam through a partnership with THACO, the F30's production is a highly automated yet meticulously supervised process that ensures exceptional quality, performance, and elegance. This detailed overview outlines the key stages of manufacturing the BMW 3 Series F30 from initial design to final distribution, highlighting the sophisticated techniques and rigorous standards that define BMW's production excellence. The journey begins with the design and planning phase, a critical step that sets the foundation for the F30's development. BMW's engineers and designers employ advanced computer-aided design CAD software to create precise 3D models of the vehicle, encompassing every detail from the chassis and body to the engine and interior components. These models undergo virtual simulations, including crash tests and aerodynamic analyses, to optimize safety, fuel efficiency, and the sporty handling synonymous with BMW's efficient dynamics philosophy. The F30 introduced groundbreaking features such as hybrid powertrains and the Gran Turismo F34 variant, requiring tailored designs for sedan, touring, and hatchback configurations. To validate the design, BMW constructs prototypes subjected to rigorous real-world testing, including high-speed track runs, extreme weather conditions, and durability trials. Data from these tests inform final refinements, ensuring the F30 meets BMW's exacting standards before transitioning to mass production. Once the design is finalized, the production process moves to material preparation and component manufacturing. BMW sources high-quality raw materials, primarily high-strength steel and lightweight aluminum, from trusted global suppliers adhering to strict quality protocols. Steel is used to craft a robust yet lightweight chassis, enhancing structural rigidity and safety, while aluminum is employed for components like the hood, doors, and suspension parts to reduce weight and improve fuel efficiency. These materials are processed at BMW's facilities, where massive hydraulic presses, guided by automated systems, stamp metal sheets into precise shapes with tolerances measured in millimeters. Simultaneously, critical components such as the 2.0L twin-power turbo engine, featured in models like the 320i and 328i, transmission, suspension systems, and interior elements, are produced at specialized plants. Each engine component, from pistons to turbochargers, undergoes meticulous inspection to ensure optimal performance and longevity, reflecting BMW's engineering prowess. The assembly of the chassis marks a pivotal stage in the production process. Stamped metal panels are transported to an automated welding line, where advanced robotic systems employ laser welding and spot welding techniques to join components into a cohesive chassis structure. These robots, controlled by sophisticated computer systems, ensure each weld is precise, contributing to the F-30's exceptional rigidity and crash safety. The chassis design prioritizes a lightweight yet sturdy framework, enhancing both handling dynamics and occupant protection. Post-welding, the chassis undergoes a corrosion prevention treatment, submerged in chemical baths and coated with an electrophoretic primer that bonds to the metal surface, safeguarding it against rust and environmental wear. This meticulous process ensures the F-30's durability, even in harsh climates. Painting is one of the most intricate and time-intensive stages of production. The chassis is thoroughly cleaned to remove dust and contaminants before entering automated paint booths. Here, robotic arms apply multiple layers of paint, primer, base color, and clear coat, with unparalleled precision, ensuring a flawless, glossy finish. A unique feature of the F-30's painting process is the robot's ability to open doors and hoods, allowing uniform coverage of interior surfaces. BMW offers a range of color options, including mineral white, black sapphire, and photonic blue, catering to customers' personalization preferences. After painting, the chassis is baked in high-temperature ovens to cure the paint, enhancing its durability and resistance to scratches and fading. This stage not only elevates the vehicle's aesthetic appeal, but also protects its exterior for years to come. Following painting, the vehicle advances to the assembly line, where a harmonious blend of automation and human expertise brings the F-30 to life. Industrial robots install major mechanical components, such as the engine, transmission, and suspension systems, with pinpoint accuracy. Meanwhile, skilled workers handle tasks requiring finesse, such as fitting the dashboard, installing premium leather seats, available in finishes like black, Canberra beige, or mocha. And integrating high-end features like the M-Sport steering wheel, iDrive infotainment system, and Harman Kardon audio system. Attention to detail is paramount, with artisans meticulously inspecting elements like seat stitching and interior trim to ensure a luxurious, flawless cabin. The F-30's interior is designed to balance sportiness and sophistication, offering customizable options that reflect BMW's commitment to driver-centric excellence. Quality assurance is a cornerstone of the F-30's production process. Each completed vehicle undergoes a rigorous inspection regimen to verify its performance and reliability. Diagnostic machines are connected to the car's onboard systems, scanning for errors in the engine, electrical components, and advanced safety features like park assistant, lane departure warning, and 360-degree cameras. Workers conduct visual inspections to confirm the absence of defects in paint, interior fittings, or mechanical assemblies. The vehicle is then subjected to a factory test drive on a dedicated track, where engineers evaluate critical parameters such as acceleration, braking, suspension response, and cabin noise levels. Vehicles that meet BMW's stringent standards are approved for packaging, while those with minor issues are returned for corrective measures, ensuring no compromises in quality. The final stage involves packaging and distribution. Approved F-30s are meticulously cleaned, wrapped in protective materials, and stored in secure facilities awaiting shipment. BMW's global logistics network efficiently distributes vehicles to dealerships worldwide, ensuring timely delivery to customers. In Vietnam, THACO oversees the distribution of locally assembled models like the 320i and 330i, which maintain the same quality standards as their German counterparts while offering competitive pricing. This localized assembly reflects BMW's strategic approach to meeting regional market demands without sacrificing its brand promise. The Michelin Research and Development Center is at the forefront of tire innovation, combining advanced materials, science, digital simulation, and sustainable practices. Located in Clermont-Ferrand, France, the center employs thousands of engineers and researchers who focus on enhancing tire performance, safety, and environmental impact. Cutting-edge technologies, such as 3D printing and AI-driven design, are used to develop next-generation tires. The center also emphasizes recycling and bio-sourced materials, aligning with Michelin's vision for sustainable mobility. Collaborations with universities and industry partners further support Michelin's goal of creating smarter, safer, and more efficient transportation solutions. The Tesla Crash Test Lab plays a crucial role in ensuring the highest safety standards for every vehicle. Located along a 340-foot track, test cars are propelled toward a solid wall using dual-model South Performance drive units connected to a steel cable system. Before any physical prototype is created, Tesla engineers perform thousands of crash simulations using 3D models and advanced mathematical tools to replicate crash physics. A standout safety feature is the Model 3's uniquely designed front passenger airbag, optimized for oblique impacts. Tesla's commitment to safety is validated by real-world feedback from survivors who credit the vehicles with saving lives. Creating a high-performance racing cylinder is a detailed, multi-step process that ensures the cylinder meets the high demands of professional racing engines. The process begins with engineering, where the cylinder design is carefully developed using computer-aided design (TED) software. The design must meet specific performance criteria, such as optimal airflow, heat resistance, durability, and strength, to withstand the extreme conditions of high-speed racing. After the design is finalized, the next step is prototyping and tooling production, where prototypes are made to test the design and ensure it functions as intended. Specialized tools are then created to facilitate efficient and accurate production. A sand core is also made during this phase, which is used in casting to create the internal features of the cylinder, including the combustion chamber and ports. Once the prototype and tools are prepared, the casting process begins. In this stage, the cylinder is cast using high-quality materials, typically aluminum or other alloys, that are able to endure the high-pressure environment of racing engines. The sand core is placed inside a mold, which shapes the internal features of the cylinder, while the external parts are molded with high precision. The casting must be flawless, as any defects could significantly affect the cylinder's performance and durability. After casting, the cylinder moves to the machining stage, where it undergoes a series of processes to refine its dimensions and smooth the surface. CNC machines are used to ensure precise measurements and finishes, ensuring the cylinder meets the required tolerances. This stage is crucial in eliminating any rough edges or imperfections that may affect the cylinder's overall function. Once the machining is complete, the cylinder ports are deburred, which involves removing any sharp edges or excess material left from the casting and machining processes. Smooth, clean ports are essential for optimal airflow and engine efficiency. The next step is nickel plating, a process in which a layer of nickel carbide and silicon is applied to the cylinder. This plating significantly improves the cylinder's durability by increasing wear resistance, reducing friction, and enhancing thermal conductivity. The plating is carefully controlled to ensure it meets the required hardness and corrosion resistance, critical for maintaining performance in racing conditions. After Nikasil plating, the cylinder undergoes honing, which involves using abrasive stones to refine the surface and create a smooth finish. Honing ensures that the cylinder walls are even and precise, which is important for achieving a proper seal with the piston rings. Reducing friction and improving engine efficiency. Finally, the cylinder is assembled with the piston and exhaust valves. This assembly is done with careful attention to detail to ensure that each component works together smoothly. After assembly, the finished cylinder is packaged to prevent any damage during transport, ensuring it arrives ready for installation in a high-performance racing engine. Transporting wind turbine blades is a complex and carefully coordinated process due to their large size and weight. These blades are essential components of wind turbines, and their transportation requires specialized equipment, such as heavy-duty trucks, barges, or cranes. The journey typically begins at the manufacturing plant, where the blades are fabricated, packed, and prepared for shipment. Given the enormous size of wind turbine blades, transport via road can be challenging. Routes need to be meticulously planned to ensure the roads and infrastructure can support the weight and dimensions of the blades. Special permits and coordination with local authorities are often required to ensure smooth transit. In many cases, wind turbine blades are transported via waterways using specially designed vessels that can accommodate the significant load. Once the blades reach their destination, cranes or large lifting equipment are used to unload and install the blades onto the turbine towers. Throughout this process, safety is a top priority to prevent damage to the blades and ensure the safety of workers and the public. Additionally, environmental considerations are taken into account to minimize any potential impacts during the transportation process. The Kiro Crane Union KSC 900 is a highly specialized rail-mounted crane designed for heavy-duty lifting and track maintenance tasks in the railway industry. Renowned for its robust performance, this crane is ideal for operations in confined or restricted spaces, such as single-track lines and areas with limited clearance. Its versatile design allows it to operate efficiently without encroaching on adjacent tracks, making it a valuable tool for tasks such as switch construction, track and bridge building, and accident recovery operations. One of the unique features of the KSC 900 is its ability to carry heavy loads in front of its buffers, while being able to slew sideways, enhancing its operational flexibility. This characteristic is particularly useful when planning logistics for track maintenance activities like switch renewals. The crane is also equipped with a telescopic counterweight system, which can be laid down during transportation, ensuring it fits within railway structure gauges, making it easy to move between different work sites. The KSC 900 is part of Multitasker series, which includes a variety of models designed to handle specific lifting capacities and operational demands. For example, the Multitasker 1000 model can lift up to 100 to 150 tons, with a maximum load moment of 1,000 to 1,200 TM. These cranes come with various configurations, including 8-axle setups, providing optimal balance and stability during operations. With these features, the KSC 900 is a key asset for railway construction, maintenance and recovery operations, offering both efficiency and reliability. Kiro's design focus on multitasking ensures that the KSC 900 can be used in diverse environments, contributing to the efficiency of railway infrastructure maintenance and reducing operational downtime. In December, the cargo vessel M/V Cabrera, a 1,768 gross ton freighter flying the Togo flag, ran aground off the rocky coast of Andros Island, Greece. The ship was en route from Cyprus to Tunisia, transporting military vehicles and related cargo when it encountered heavy weather. Strong winds and rough seas drove the vessel onto submerged rocks, where it sustained critical hull damage and eventually broke in two. The incident posed a significant environmental threat due to fuel leakage, debris, and the potential contamination of the surrounding marine ecosystem. To respond to the situation, Greek salvage company MEGATUGS joined forces with SimIT Salvage, a division of Royal Boskalis Westminster and one of the world's leading maritime salvage firms. Their cooperation brought together local knowledge, international salvage expertise, and the logistical strength necessary to handle such a demanding operation. The salvage effort was carried out in three primary phases: pollution prevention, cargo removal, and wreck dismantling and recovery. Each stage required detailed planning, skilled personnel, and highly specialized equipment. Pollution control was the top priority. The wreck still contained substantial quantities of heavy fuel oil and lubricants that, if spilled, could severely damage the pristine waters of the Aegean Sea. Divers worked in challenging underwater conditions to seal breached fuel tanks and deploy pumping systems. Floating booms were positioned around the wreck to contain any leakage. In total, over 50 metric tons of pollutants were safely extracted from the ship, preventing widespread environmental harm. Following containment efforts, the focus shifted to cargo removal. The Cabrera had been transporting several military trucks, armored vehicles, and spare parts. A floating crane barge was brought in to lift each unit from the wreck. Precision was critical, as mishandling could have caused further damage to the wreck or the seabed. Despite the complexity of this stage, all cargo was successfully recovered and transported ashore for inspection and disposal. The final and most labor-intensive phase was wreck removal. With the ship broken into two main sections and resting on a rocky, uneven seabed, Dismantling the structure required the use of hydraulic cutting tools, underwater wire saws, and in some cases, controlled underwater charges. Divers and engineers carefully separated the wreck into manageable sections. Each piece was lifted using heavy lift pontoons and barges before being taken away for recycling or safe disposal. Throughout the operation, environmental protection remained a priority. Water quality monitoring was conducted continuously, and all work complied with Greek maritime regulations. Despite adverse weather and the hazardous condition of the wreck, the project was completed in just over 4 months without any major incident. The successful removal of the M/V Cabrera stands as a prime example of how international collaboration, technical precision, and rapid response can come together to resolve complex maritime emergencies.